Welcome to my talk about the combinatorial design of high-entropy alloys. In our institute, we work with a relatively big team on a variety of topics related to high-entropy alloys, and I show here an overview diagram which shows some of the fields we work on, like magnetism, mechanical properties, basic alloy design, but also on corrosion properties and on catalysis. And I will highlight the contributions of all these outstanding colleagues as we go along. Let me first share with you some of the basic alloy design criteria that we use. We use, on the one hand, the so-called mechanical metastability criterion, such as shown here in a free energy diagram, where you keep your concentration but athermally change from one state to another. A second approach is the so-called chemical metastability criterion, which for instance can refer to the mechanism of spinodal decomposition. Mechanical metastability unleashes a variety of transformation opportunities, such as martensite formation, and I will show some examples in the following. The specific feature of such isothermal transformations is that they are not affine, not commensurate, and often create very high misfit deformation, as you see here in this little In-situ TEM movie, where you see a high population of dislocations emerging from the tip of a progressing martensite. That means with the mechanical metastability criterion, you can often achieve a very high combination of coexisting strain hardening mechanisms. Another interesting aspect related to mechanical metastability in that context is the confinement. You see here an example in this TEM in situ study that a dislocation has to expand and grow inside of a confined region that is formed by a twin. And that gives you a number of size effects in such alloys. One of the most important parameters that you tune in the field of alloy design for high-entropy alloys is, of course, the stacking fault energy. The stacking fault energy does not only act directly on the twin formation, but it acts in multiple ways. It affects the dislocation slip and, of course, the stacking faults, the distribution and number of stacking faults. Through the change in the cross-slip behavior, the stacking fault energy also affects the formation of the dislocation cell structure, of course. And, of course, the population of partial dislocations, reduced cross-slip and planar slip is also affected by this value. Another feature that becomes very important for high-entropy alloys is chemical short-range ordering, and it also affects, of course, the stacking fault energy locally. Stacking fault energy changes can also lead to changes in the slip band formation and in the so-called dynamic slip band refinement mechanism when you have more confined and parallel slip bands. Then, of course, when you reduce the stacking fault energy even further, you get to mechanical twinning, which is one of the most important mechanisms that you can unleash in that context. And you can get into regimes where different phases can coexist. This is very important. When you have very low stacking fault energies, you can find in one and the same material phase-centered cubic, hexagonal, body-centered cubic, and alpha prime, so distorted tetragonal phase contributions. So you do not only create by that the unidirectional trip effect, that means the formation of epsilon or alpha martensite, but you can also render bidirectional trip effects. That is an effect where you can forward and backward activate these athermal transformations, and we will show you later some examples how that has been realized. So some of these mechanisms are now shown here along the arrow of the reducing stacking fault energy related to the mechanisms that I've just mentioned before. And you can see the direct combination between, for instance, the onset of mechanical twinning and the value of the stacking fault energy, such as shown here. The same applies for the onset of epsilon martensite formation and growth, where you see a direct combination between its activation stress and again the stacking fault energy. So you see, you can put this knowledge into maps such as shown here, for instance for the case of manganese and carbon, and calculate the corresponding transformation free energy values, which then can be used to create treasure maps for unleashing these different mechanisms. And that is a big advantage of the high entropy alloy design, namely the design towards a certain desired value of the stacking fault energy, which then allows you to activate a variety of these mechanisms. That has, for instance, been realized in a number of alloys based on the iron, manganese, carbon, aluminum system, which are also referred as lightweight steels. Here's an example, not yet from the high entropy family, but from a classical TWIP steel. You see the composition is 22 manganese and 0.6 carbon. And you see this enormous strain hardening of this material due to twin formation in the true stress-strain curve. When you follow the actual strain hardening, such as shown here, and highlight the individual transition regimes, that you see that in the beginning you have first very complex dislocation cell formation activities, and only at the somewhat higher deformations, where you already reach the second plateau in the total strain hardening behavior, you arrive at a very, very fine twin structure, as shown here, by use of electron channeling contrast imaging. So when we change this alloy composition even further, here with 30% manganese and 2% aluminum and 1.2% carbon, so very high carbon content, you have even a more complex strain hardening course, as you see here, with two plateaus, one being here, one being here. And when you again follow in detail with a transmission electron microscope here the dislocation and twin substructure evolution, then you realize that the first plateau, the first strain hardening plateau, is more triggered by the population of high density dislocation walls, and only the second plateau at very high loads is due to the onset of mechanical twinning. That means you use the global alloy composition to shift the transition for the onset of twinning from lower loads to higher loads. That means you create strain hardening at the later stages of deformation where it is really needed. And that is, of course, really possible in the field of high entropy alloys, where the compositional range to modify these stacking fault energy values is so huge. In the case when we stay for a second of more steel-related variants of that, then you see that this, for instance, allows you to drastically reduce the mass density of such steels, which can unleash twinning or trip effects over a wide range of aluminum, manganese, and carbon content. Now let me get a little bit deeper into the alloy design directly related to high entropy alloys. In the ideal case of the original idea of the high entropy alloys, you have, from an assembly of several elements, as shown here, a completely random solid solution with a maximum contribution in the isostoichiometric composition that gives you a random solid solution with desired properties. So this was the original idea, but you can also arrive in areas of the phase diagram where you create a Landau form in your potential and a spinodal decomposition. Well, and you can even, as I show later, create alloys where you have several coexisting solid solutions, such as shown here, with in part individual properties that you can fine-tune by adjusting the alloy. And of course, what is very often encountered is that you have intermetallics sticking out by purpose or not by purpose that can change your properties. So it's a wide variety of opportunities for alloy design. When you bring these alloy design concepts together, namely the one from the high entropy side, where we have a lot of chemical freedom to tune the stacking fault energy, the spinodal, the misfit, and so on. And when you bring this together with mechanical alloy design ideas that I have shown before, related to athermal transformations such as twinning, martensite formation, but of course also precipitate formation, then you bring, so to say, the best of these two worlds really together. And that means you can, by combining the compositional degree of freedom from the world of high entropy alloys and the mechanistic alloy design, such as, for instance, from athermal transformation, can create a wide family of high entropy alloys such as TWIP high entropy alloys, TRIP high entropy alloys, and so on. So that is kind of the philosophy behind our alloy design strategy. That means you use the high entropy concept to shift compositions into thermodynamic stability regimes to trigger specific mechanisms that you want, and you do not exploit just the solid solution but also the metastability behind the phases that you have created. Let me go a little bit deeper into the thermodynamics for a moment. When you, of course, have an equimolar composition, then you have the highest contribution of the mixing entropy, such as shown here. When you deviate from that equimolar composition, the absolute value is of course a bit smaller, as you see here. However, the variation as a function of compositional changes is not so drastic. That means once you have deviated a little bit from the iso composition, high entropy alloys, you have a wide flexibility to adjust your compositions by minimal losses of entropy. And we realize many of such alloys in a bulk form, as you see for instance here by combinatorial casting, where through an UHV valve, vacuum valve, we can adjust the corresponding alloys, but in a form of big blocks where we can roll them and heat treat them. And that allows us to access bigger maps of variants in the mechanical properties, such as shown here. And you see, like shown before, for this specific alloy family, we were capable of changing the alloys from predominant dislocation slip towards additional activation of twinning and nanotwinning, towards even activation of the TWIP effect, depending on the exact composition. Let us look for a moment a little bit closer into the thermodynamics. Here we have, for this specific composition, plotted the entropy, the effect of the entropy contributions versus the change in the nickel versus the iron content. And what is very interesting to see that the classical mixing entropy is of course the same for the FCC and for the HCP lattice, but the vibrational and magnetic contributions are different, as you see. And only if you really consider all three contributions, that means the mixing entropy, the vibrational entropy, and the magnetic entropy, then you are capable of really describing the free energies of these coexisting phases, and also the staking fault energy, of course. So we have realized these fully DFT calculated values, considering all three entropy contributions, and have compared that to experiments such as shown here. And indeed, the experiments are in excellent agreement with these theoretical predictions. And then we pick the alloys that we show here, which are characterized by the coexistence of two of these high entropy phases, namely one with FCC and one with hexagonal lattice structure. And when we go a little bit from the X-ray diffraction to the microscopy, then you can indeed see here in the EBSD map the coexistence of these two phases. When you then run ADX maps on that, you indeed see that at this mesoscopic scale, they are both completely random solid solutions, but they coexist. And from that, you can obtain in part extremely good mechanical properties, such as shown here, with an increase of both the ductility and the tensile strength, which is in part due to the very strong TWIP effect in these materials. As I will show later in more detail, the TWIP effect, that means the transformation from the FCC into the hexagonal phase, does not only take place here at this mesoscopic scale. When you follow here the EBSD maps, you can nicely see that, but it also applies to very high resolutions where this change from FCC towards ACP takes place at a very fine scale also. When you blow this up here a little bit and again conduct corresponding chemical analysis, you see still here in these EDS maps that have been taken in STEM how both phases are indeed solid solution, randomly solid solution alloys. And this also can be shown here by atom probe tips, which have been really taken across this interface between the FCC and the hexagonal phase structure. You can see that they are both really regular solid solutions. And what I mentioned before is really interesting. When you now stay inside of such an epsilon area, you can see that nanoscale gamma lamellae form in them under the effect of external loads. And the same is shown here at atomistic resolution, where you see that inside of the epsilon blocks you can have formation of gamma layers, as you see when tracking here the positioning of the densely packed planes from a CB-CB sequence towards an ACB-ACB sequence. And we find these relations for different layer thickness from 4 to 16 layers and so on. That means we find this formation of the gamma lamellae inside of these epsilon blocks down to the atomic scale. That means at this scale you could also say the material does not really care what its exact lattice structure is. Interestingly, you find the same thing inside of the gamma blocks. Now we are sitting in an FCC area of the material, and you have the same phenomenon, namely that it can locally go from the phase center cubic structure to an epsilon structure, such as you see here. Again, for different sizes of these lamellae. That means you have an atomic scale refinement both of the gamma by epsilon and of the epsilon blocks by gamma. That means the coexistence of these two phases really is refined towards near atomic scales. And that gives, of course, rise to an enormous hardening of the material, because all these interfaces, of course, block the penetration of dislocations. What is very interesting when you look into an in-situ TEM experiment, such as shown here, then you see a very complex microstructure evolving, again like shown before, with the interplay of the FCC and the hexagonal phase. And if you now follow with a couple of snapshots an increasing load, as you see here, you find an interesting phenomenon, namely the formation of the HCP areas, like indicated here by these yellow arrows, which, when you go on loading, are removed again. That means these leading dislocations return due to local stress changes, and then this formerly formed HCP area is removed and a twin is formed. So that's very interesting that certain transformation phenomena can be formed and can be removed in the same sample. That means it's kind of a reversible effect. Now we switch gears and come to functional properties. Here's an alloy family based on the iron, cobalt, nickel, manganese, copper system. And we do this to show that by a decomposition, by a well-designed chemical decomposition treatment, you can arrive at really interesting hard magnetic properties with the system. Here we show an example as we homogenize and then heat treat this material here at 200, 600, 700, 800 degrees and so on for different times. And you can start to realize here a very fine formation of a spinodal substructure. Now this is shown here in higher resolution with 50 nanometer resolution for the 700 degree case, and it also shows that you have a chemical decomposition. This is shown here with a somewhat better resolution. You see that on the one hand the copper is decomposing and the iron, cobalt, nickel and manganese are agglomerating. So that gives you a very finely subdivided spinodal structure, where you see that both have at very high resolution, have a high distortion, but are otherwise isostructural. This is shown here in the atom probe analysis, where you can nicely see, highlighting here the copper for instance, how this substructure looks like. And again, you can nicely realize the formation of very fine channels where the copper is enriched, and the other channels where the iron, cobalt, nickel, manganese is enriched. This is shown here in a 2D diagram with the same content, namely very strong peaks of copper, of course also with some nickel and manganese partitioning, but otherwise these elements go mainly between the copper. So we have very fine decomposition. We follow this again with atom probe investigations at 600 degrees centigrade now for 6 hours, and you can see how the substructure forms and coarsens. What is really interesting in this context is now to track the magnetic properties during this decomposition. This is shown here in terms of the magnetization versus the annealing time, and the blue data reveal the Curie temperature as a function of the heat treatment time. And you indeed can see that for a certain decomposition aspect ratio, you can form an enormously high Curie temperature and very high magnetization if you look at these values. So it makes this material class indeed very attractive for hard magnetic fine-tuning. Now interesting is the interface spinodal when you start playing with these chemical compositions in the high entropy family. And we look at the Cantor alloy composition, so the iron, manganese, chromium, nickel, cobalt family, that you form very strong decomposition and particles even at the interfaces. So that was long known and shown by Otto and Iso George and others. But what is really interesting is that when you look inside of the grain boundaries, now inside of the grain boundary planes, prior to formation of these intermetallics, you find a very strong undulation of the concentration. Here shown exemplary for the nickel and here for the manganese. And when you appreciate this legend, then you can see that you have a very strong variation from like 15 up to about 40% variation in the grain boundary plane. So it means there's a spinodal decomposition wave that happens on the grain boundary. This is a schematical sketch that explains this context. Here you have a grain boundary and some solid solution atoms, and you have a course like shown here. When you give the system some heat, then you get a classical decoration of the grain boundary and you get a course of the concentration such as shown here. As this is an equilibrium segregation, the chemical potential remains constant during that time. However, when you translate this in a hand-waving fashion into a bulk phase diagram, then you realize that the original composition was in the solid solution state, while the new chemical working point that you see here is suddenly, for instance in this example, in a spinodal decomposition range. That means in one and the same material, when you have highly decorated defects, you can suddenly find your defected area in a spinodal decomposition regime. It is clear that this schematic that I show here is a bit hand-waving because we all know that these phase diagrams are actually not made for defects, but they apply only to the totally defect-free bulk material, but it gives you a certain direction of how to understand the thermodynamics behind such segregation. When you translate this into the classical isotherms, this amounts to saying that you do not follow a classical Gibbs adsorption isotherm, but rather those that include interactions of the segregating species, turning it into the Fowler-Guggenheim or Hart or Goodman isotherms. Now, towards the end of the presentation, let me talk a bit about the role of interstitials. Interstitials in high entropy alloys are very interesting for a variety of reasons. We talk here mainly about carbon, nitrogen, oxygen, boron, and of course hydrogen. And the interesting aspect associated with interstitials is that they can create very high lattice distortions, often much higher than those created by substitutional elements. And they can have a very strong thermodynamic effect on the system because they have less metallic bonds. And they affect, of course, phase transformation, both thermally and athermally, and the kinetics of the phase transformation also. What is also very interesting when you play with interstitial elements is that you can decouple the kinetics. That means you have slow diffusing, often substitutional elements in the material, but you have also very fast diffusing elements such as carbon, nitrogen, or hydrogen. So that means you can modify a system by a sequence of different heat treatments where you exploit the different diffusivity of the interstitials and substitutionals. It is of course also clear that they can form brittle phases instead of solid solutions above certain critical values because they have less metallic bonding contributions. However, this is knowledge from typical interstitial systems where the interstitials are surrounded by a very symmetric environment of the matrix. But in high entropy and medium entropy alloys, the local environment is often neither chemically nor topologically symmetric. And that makes it very interesting because these matrices can break the symmetry and by that also increase the solubility limits for interstitials. And the question is, can this solubility limit by all these considerations, or due to all these considerations, be pushed to higher values? Let us first take a look at the effect of hydrogen. The main idea is, of course, originally not to have it as an alloying element, but you can see it a little bit in that way when you look at the high resistance of this high entropy against hydrogen charging. Typically, you encounter very strong embrittlement of these materials when exposed to hydrogen, but for some high entropy alloys, like the equimolar-FeNiCrMnCo alloy shown here, we find even a slight increase in strength and ductility when charged by hydrogen. We attributed this to the formation of nanotwins. Here are some reference examples from the family of superalloy, the Inconel 718, and here from stainless steel, which both show a somewhat stronger reaction when charged by hydrogen. So this is an avenue that we pursue further to see whether we can identify certain high entropy alloys with a very high resistance, not only to corrosion, but also to hydrogen embrittlement. Some ongoing work from my colleagues Liu and Wu is shown here. Namely, they have chosen the system titanium, niobium, zirconium, blended with very high concentrations of oxygen, carbon, and nitrogen, and tried to see what these types of solid solution can offer in terms of properties. What is very interesting when you have here an example with 12 atomic percent interstitial oxygen, that you indeed do not form oxides. Otherwise, you might expect that in a matrix that contains titanium and zirconium, but we don't find that. And here are some distribution functions from atom probe analysis, which again, like this diagram, confirm that there are not oxides formed, but the oxygen is indeed in solid solution in this material. When conducting pillar experiments, such as shown here, you see the appreciable strength increase when blended by 6% oxygen and by 12% oxygen. So you see that the yield strength has, of course, strongly increased, but also the strain hardening is much higher than that of the base reference alloy, which would be the medium titanium niobium zirconium alloy without any interstitial doping. It is very interesting that you see here at a higher load that you form, for instance, stacking faults in this material, and you form also nanotwins in this material, like nicely shown here. And you see this is a 60 nanometer space bar, and that means you find an enormous refinement of the matrix by these defects. Here you see two consecutive snapshots from a movie where stacking faults are formed and twins are formed with a very high refinement of the matrix structure, however here shown at a very high resolution. So with that, I come to the end of my little presentation today, where I tried to show you some of our ideas in the field of high entropy alloy design. I shared with you some ideas about the basic alloy design philosophy that we adopt in terms of exploiting multi-component thermodynamics. Also, when you remember the spinodal at grain boundaries, low-dimensional thermodynamics. And the last but not least point was exploiting the change in the limits of interstitial blending. So we find that this is a very avenue for the future. And in terms of properties, we discussed mechanical features, but also aspects such as magnetism or resistance to hydrogen embrittlement. And with that, I thank you very much for attending my presentation, and I would be happy to take any questions. Thank you very much.